Hello everyone, I'm Liu Liang from Tianjin University of China, and it's my pleasure to share our work, Opponent Modeling with Trajectory Representation Clustering. My presentation contains the following 4 parts: background, method, results, and conclusion. First, introduce the background of the problem. The non-stationary problem has been one of the most challenging problems in the field of multi-agent system. It is concerned with how an agent responds optimally to an opponent when the opponent policy is constantly changing. A great deal of previous research has focused on modeling the opponent policy explicitly or implicitly, but ignoring the significance of data balancing for continued response to the opponent policy. Specifically, the first-in, first-out experience replay mechanism leads to an imbalance in the dataset when the frequency of occurrence of a certain opponent policy decrease, which leads to a series of catastrophic consequences such as strategy forgetting. This is the motivation for our study. Next, the methods section. Our method is based on contrastive learning and self-supervised distinguish different opponent trajectories. Each trajectory is encoded by CPC. The observations are encoded as ZT through MLP, and the ZT of the first t-step are encoded as the context information CT through a GRU, and we use a bilinear product function as the similarity function, and the influence AE loss as a loss function. This loss function represents an increase in the similarity of predictions for one's own future trajectory, while decreasing the similarity of productions for other future trajectories. Then we can map trajectories to points on the representation space. We then use a simple Euclidean distance to calculate the trajectory distance and distinguish them by agglomerative cluster. When popping trajectory data from the replay buffer, we will select from the largest class as much as possible, thereby increasing the proportion of data of the class with small occurrences. Combined with the reinforcement learning algorithm SAC, the schematic diagram of the entire algorithm is as following. Reinforcement learning and contrastive learning are interactively performed, and the frequency can be adjusted. From the experimental results, it can be seen that our method outperforms vanilla SAC and also outperforms existing opponent modeling algorithms, DRON and DPIQN. This is due to the fact that we keep the data balance in the replay buffer. When the proportion of a certain type of opponent policy data in other methods decreases to 5% as its frequency decreases, our method still maintains its proportion of 13% to 50%, thus avoiding strategy forgetting. In conclusion, there are two contributions in our work. Interaction trajectories are self-supervised encoded through a contrastive learning algorithm so that different opponent policies can be more accurately represented and distinguished in the representation space. And from the perspective of balancing data types, artificially retain the types of data that account for a small proportion in the replay buffer to avoid catastrophic policy forgetting. In the future, we would like to combine multitask learning algorithms to learn different opponent policies as different tasks, and to explore more efficient ways to distinguish opponent policy. That's all. Thank you for listening.